We don't need to get into this right now, but because string or M theory, it remains controversial among physicists. I always find it fascinating to hear why some physicists gravitate toward it when others don't. And over the past couple of decades, you've been one of the central figures in the area. So I can't help but ask just what sorts of considerations, I mean, whether they're philosophical, mathematical, physical, or otherwise, led you to gravitate toward it already when you were in graduate school?
Well, I should say that before we talk about string theory, let's try to explain the problem that it tries to solve. So it's the problem is to understand the quantum mechanics of space-time. So Einstein's theory of gravity consists of the idea that space-time is curved and dynamical. It can change and so on. But it's a classical theory. So in the sense of classical mechanics, it's a classical, let's say, field theory. On the other hand, we know that matter at short distances is described by quantum mechanics, a new type of law. And other classical field theories, such as electromagnetism, that describes the electromagnetic field, are really fundamental, that are changed by quantum mechanics and are and that's important. I mean, we describe interactions of matter with light using this quantum theory. So the question is gravity also quantized in a similar way? And what are the formulas that describe this new quantum theory? Now, let me say why we care about this problem, why we care about the quantum theory of gravity. Now, for most practical purposes, we don't care. So if you are interested in building a better iPhone, or you are interested in some very practical technology, it's going to be totally useless. And the reason is that gravitational coupling is very small, and that this makes these quantum effects very small. However, quantum gravity is important for understanding certain processes in the universe, in particular in very extreme conditions. So, for example, what happens in the interior of black holes where the universe inside the black hole collapses, or what happens at the very beginning of the Big Bang, perhaps even before inflation, when you had this initial cosmological singularity or some region. Singularity means that we don't understand it using the Einstein theory of gravity. So we need this. We think that if we had the quantum version of the theory, then it would be non-singular. It would be something that we could understand. So, in fact, this problem of the beginning of the Big Bang is the most interesting problem that quantum gravity could address. Other problems, as I said, were problems involving black holes. So that's the context. That's why we want a theory of quantum gravity. Now, theories like electromagnetism have been quantized, or the quantum theory was developed using a certain type of technique. And the same type of techniques do not quite work for gravity. And so that's some background. So I gave you why we care about this theory, and second, why the simplest approach doesn't work. I mean, the simplest approach works for some things. So in some approximation, it does work, and it predicts some interesting things. For example, that if you have the theory of inflation, which says that you have some very rapid expansion at the beginning of the universe, then quantum effects should produce gravity waves. So if people are trying to look for them mainly through
I'm talking to Brian Keating tomorrow about this, actually.
Wonderful. Yeah. So it's something that could be detected at any time. I mean, there was a claim of detection a few years ago. Unfortunately, it was incorrect, but by BICEP, and that kind of shows you that they could be detected at any time. And if they are detected, then it would be a real smoking gun of quantum gravity, that gravitational fields should be quantized. I mean, we are assuming the theory of inflation, but yeah, And for that, you don't need string theory or any fancy theory. So it's just the simplest quantization is fine. So the place where you need it is when you try to get something a little more precise or in more extreme conditions. So inflation happens, the expansion of the universe is rapid, but it's not that rapid compared to what we call the Planck scale, which is the scale at which quantum gravity effects are very important. So if we want to somehow go earlier than inflation, then we would need the theory of quantum gravity, and we would need some better theory. Now, string theory is a theory that had a long history, and it originated originally as a theory of the strong interactions, and it was originally based on the idea that instead of particles, we'd consider strings. That's where the name comes from. And this theory was developed, and over the years, then people realized, Yonea and Schwartz realized that it could be used to describe gravity, quantum gravity. And when you use it for that purpose, it leads to well-defined formulas, and it doesn't have the problems that the standard techniques that were used to construct gravity. So you don't have those problems. So at the very least, I think you should think of string theory as a kind of toy model for quantum gravity. So it's a particular version of quantum gravity that seems to be well-defined, where you could compute corrections to any order and defines a kind of what we call a perturbation theory, similar to how we define, let's say, quantum electrodynamics, so the theory that describes the interactions of quantum light with quantum matter. But it's a little more complicated, and it has some various features, and it put some constraints on the solution. So the simplest flat space-time needs to have a specific number of dimensions, let's say 10 dimensions. So it's a very constrained structure, let's say, fairly constrained, and the fact that it's well-defined then allows you to somehow study within this theory various questions relevant to quantum gravity. In particular, it was useful for understanding aspects of black holes. Now you might ask, well, so let me say what string theory has done and what it hasn't done. So it has provided some nice explanation for quantum aspects of black holes. I'll get more into that later. And something that it has not done yet is to understand the beginning of the Big Bang. For example, what cosmology would look like in string theory. So it's a complicated theory. We don't understand it completely. We understand some aspects of it. And at the very least, it's a toy model. There might be other theories of quantum gravity that are that exist, make mathematical sense, but the theory that makes most mathematical sense so far is string theory. So no other theory on the market sort of comes close to it. But yeah, there might be other theories, and maybe we might discover them. And one of the things that has happened is that there were historically other approaches to quantum gravity that people had. For example, 11-dimensional supergravity. And this was thought to be different from string theory and unrelated, and some people said was wrong or so on. But then now we understand that it's kind of part of the same structure, that there is some theory that reduces to 11-dimensional super. So historically it has happened that things that were not considered string theory are now considered string theory. So I think maybe so we've expanded these horizons, and maybe we'll expand them more in the future as we understand that other ideas perhaps are we find the right place for other ideas as limits of various kinds. So mostly people who are called, let's say, string theorists are people who are interested in this problem of the quantum mechanics of gravity. So gravity and quantum mechanics, space-time and quantum mechanics. And so that's roughly what it is. What it is both from the intellectual point of view and also from the sociological point of view. So someone who works on string theory, let's say like myself, for example, I don't all the time work on the traditional string theory of the 80s. We might work on different toy models that are interesting for quantum gravity. And for example, in the past few years, we've been thinking about something called some model that was inspired by some problems in condensed matter physics. And as far as we know, it's not directly connected to the string theory, but it has some features in common, and has been very useful. So,
Well, that was a terrific introduction. And just though to recapitulate, so I should understand that your interest in string theory stems from maybe two basic considerations. One's a conviction that quantizing gravity, particularly for understanding the Big Bang, is the most important goal of theoretical physics right now. And then second, that string theory is a particularly useful way of doing this, especially, as you mentioned, for studying black holes, though it hasn't quite gotten to the Big Bang yet. And at this point, it's the best for these things mathematically, though, as you mentioned, other theories might arise.
Yeah, I wouldn't say it's the most important goal in particle in physics. Physics is very broad. It has many interesting goals. There are many interesting problems in physics. This is just one question in physics that is interesting. I find it interesting, but I mean, there are of course many other interesting questions. Another point that I didn't emphasize, but let's say was emphasized a lot in the 80s and 90s, is that we, from string theory, from the 10-dimensional theory, if we put it on some special 6-dimensional manifolds, we could get physics similar to that in our own real world. So it has the ability perhaps to incorporate the rest of physics, the standard model in particular. And there are many ways of doing this. So you can get the standard model, or you could get many other possibilities. And that might be another avenue through which you can connect string theory to reality. So far we haven't connected it, because mainly the main problem was in the beginning people thought that there would be a small number of possibilities and one of them would be the standard model. But now they realize that there are many possibilities. The number is so big that we could perhaps get the standard model, but we don't have a concrete prediction.